Yeah, good morning. This is my first time here. It's a pleasure to be here with you. I'd like to thank Professor Gustavo for the invitation. I hope not to drift too much from the mainstream discussions here as I bring an engineering biased view on the applications of commercially available solutions. And before delving into the main topic of my presentation, which is a test bed we are building at CPQD, I will start with a brief review of some fundamental concepts of cryptographic systems and how they are threatened by the ever-evolving quantum computing technology. So I'm from CPQD. We are one of the main innovation centers in Brazil, a 49-year-old company with clients in different market segments. I'm a researcher in the photonics and optical and quantum technologies, where we work with optical communications, optical sensing, and starting this year, also quantum technologies. So, as I'm sure you know, in a cryptographic system, we have a transmitter and a receiver, Alice and Bob, exchanging data over an insecure channel that may be intercepted by an eavesdropper. And then encryption and decryption operations are executed in order to prevent the confidentiality of the message to be compromised by the intrusion of by the interception of an intrusion. So there are basically two types of crypto systems, the symmetric and the asymmetric ones. In a symmetric crypto system, we have a single key used for both encryption and decryption operations. And the security of this system relies on the secrecy and the complexity of this key. If we build it with 256 bits, for instance, we would have more than 10 to the power of 77 different possibilities. Let's imagine now a cyber attack scenario using a state-of-the-art supercomputer running at 1 exaflop per second. And let's say for a moment that we could verify each key in one flop, or one floating point operation. We would still need more than 10 to 48 years to verify not the complete set, just 1% of the key space. It's almost 40 orders of magnitude higher than the estimated age of the universe to verify just 1% of all possible keys. That's why symmetric crypto systems are ultra secure. They are indeed quantum resistant. But there's a caveat here. There must be a secure way for Alice and Bob to exchange their keys. After all, the same keys are used for both encryption and decryption. And this problem of key exchange was elegantly solved in the 70s with the advent of the public key cryptography. In this asymmetric system, Bob shares with Alice his public key, which is used for encryption, and he holds its private key used for decryption. The security of the system relies on the complexity of some mathematical problems, such as the discrete logarithm and the integer factorization problem. They form one-way functions or mathematical calculations, easy to be done in one way, but very difficult or intractable to be reversed by classical computers. In practice, we use a combination of both in a hybrid crypto system, with the symmetric systems being fast and efficient, used for high-speed data encryption, while the asymmetric approach being much slower, used only for key exchange. Typical algorithms used for symmetric encryption are the Advanced Encryption Standard and the Cha-Cha-20. For the asymmetric approach, we have the classical Diffie-Hellman, RSA, and elliptic curve cryptography. This well-established and widespread crypto system is now under the threat of the quantum computers. And this threat actually depends on two factors. First is the existence of a cryptanalytically relevant quantum computer. That means a machine sufficiently developed to run the required algorithms to break crypto systems. And the second factor is the existence of the the quantum algorithms. Peter Shor created one that finds those discrete logarithms and can perform integer factorization in polynomial time, while Grover devised a new one that finds an item in a data set with quadratic acceleration. The first attacks the asymmetric systems, while the second, the symmetric ones. And to mitigate this risk, we turn to both quantum and classical approaches. There's a technique called quantum key distribution and also quantum random number generation that leverages quantum mechanical phenomena to establish or to derive pairs of identical keys or to generate truly random numbers. And we also have the post-quantum cryptographic algorithms, which, despite their name, have nothing to do with quantum at all. They are just a new asymmetric or classical asymmetric system that uses new mathematical methods or problems that are resistant to both quantum and classical attacks. We commonly group these three technologies under the terms quantum cryptography and post-quantum cryptography. So in the QKD technique, Alice prepares and transmits quantum states to Bob over a quantum channel, such as an optical fiber. They also communicate over a classical channel, which doesn't need to be encrypted, just authenticated, by which Bob sends back to Alice some information, such as the basis he used to measure those quantum states. Then, after running a special protocol, such as BB84, and after performing some post-processing operations, they can derive pairs of identical keys that are then delivered to a data layer where they are used by symmetric ciphers. The QKD technology provides truly unconditional security. That means it doesn't depend on any computing power. Quantum mechanics guarantees that any attempt to intercept and measure those transmitted quantum states would inevitably lead to the change of their properties, and this could be easily detected by Alice and Bob by observing an increase in the quantum bit error rate. By the way, this is exactly what ensures the security of QKD. QKD does not cipher messages. It's just a way of exchanging and distributing keys with a mechanism to provide the detection of intrusions. As for the quantum random number generation techniques, there are many quantum mechanical phenomena to be explored. In these diagrams, you can see a photon crossing a polarizing beam splitter or a regular beam splitter, generating quantum superposition states of either the polarization components or the transmitted and reflected path components. This is an example of the single photon detection approach. We also have many commercially available solutions exploring different mechanisms. The first two use quantum noise, optical shot noise. The third one is based on quantum tunneling in diodes, for instance, and the last one explores phase diffusion, basically turning a laser on and off to generate different phases. Finally, as for the post-quantum cryptography algorithms, we already have many standardized by NIST, the North American National Institute of Standards and Technology. The blue ones are designed for digital signature or authentication, and only a single one, the Crystal Kyber algorithm, is designed for key exchange. So in this scenario of emerging technologies, CPQD started a project in the beginning of this year called Cybersecurity in the Quantum Domain. It's funded by MSTI and coordinated by Softex, in which we'll be able to explore these three technologies in different application scenarios, such as communication systems, blockchain, IoT, and others. And most importantly, we'll build a test bed using commercially available solutions. And this test bed will be opened to the academia and to interested companies, which may bring us new test cases or their own solutions to be tested, to be validated in our test bed. So turning back to our hybrid crypto system, please remember that the symmetric ones are quantum resistant. this is just the asymmetric layer that is under the threat of quantum computers. And this is exactly this layer that can be replaced either by QKD or PQC approaches. So in this first testbed scenario, we are integrating QKD with optical transport network technologies. Here we have an OTN muxponder from Ribbon Communications. It receives a 10 gigabit Ethernet client signal, maps this client signal into an OTN signal that is transmitted at 400 gigabits per second over 200 kilometers of optical fibers. In the other end, we have another muxponder receiving the OTN signal, demapping the client signal, and delivering it to their final destination. Both units incorporate symmetric crypto engines using the advanced encryption standard algorithm. And because of that, they need identical keys at both ends. These keys would otherwise be exchanged by a vulnerable asymmetric system. But here, they are provided by a QKD solution. We are using QKD transceivers from CPQD. They implement time-binary encoding with the decoy state BB84 protocol, and they tolerate a channel loss of up to 20 dBs. That's why we need a central unit here in order to reach 200 kilometers. But it's important to note that this is not a quantum repeater. It's just a combination of a receiver and a transmitter within the same box. It's kind of like we have a second Bob and a second Alice in the same box. Let's call it Charlie for a moment. So actually we have a QKD link between Alice and Charlie, establishing a first key pair. Then we have a second link between Charlie and Bob, creating a second key pair. But remember from our test bed that we want to communicate Alice with Bob. So we need a way to forward this key from Alice to Bob. And to do that, we cannot reduce the unconditional security provided by the QKD solution. Whatever cryptographic system we choose would not match the unconditional security of QKD, except for one, the one-time pad encryption. It requires a key to be used only once, to be generated by truly random numbers, and to have the same size of the message to be encrypted. These three criteria can be easily met if we perform an XOR here, generating a third key that can then be transmitted to Bob over a service channel, which doesn't need to be encrypted. Then Bob performs again an exclusive OR, and in this way it recovers the same key used by Alice. This is exactly what happens in our test bed with a key management system embedded into the software that runs on the QKD boxes. Now we can replace the QKD approach by a PQC alternative. So here you see we are integrating a quantum random generator module to provide the entropy source for the Kyber algorithm. Then we are using this PQC algorithm to exchange keys, and then after the keys are exchanged, they are again inserted into the muxponders. We can also move from OTN layer 1 encryption to an Ethernet domain. So here we have an Ethernet layer 2 encryption. We are using a network interface card with hardware-based MACsec cryptography. MACsec also uses a symmetric algorithm, and again, the necessary symmetric keys are provided either by a QKD solution or by a PQC approach. We are also exploring both quantum and true random number generator modules with different bit rates. We are performing some entropy tests and also looking for new applications in the financial sector, in blockchain, IoT, and others. Here you see a picture of the QKD boxes in our bench. We just received the equipment 1.5 months ago. And this is our very first preliminary result. We just did a simple verification, plotting the secure bit rate as a function of the channel loss. And we can observe the expected decrease on the secure bit rate, as well as the increase in the quantum bit error rate for both the signal and the decoy states as a function of the channel loss. So, as I mentioned, the testbed is open. Contributions are very welcome, and you can bring us use and test cases, equipment and solution for integration tests, and any collaboration for educational purposes. Thank you for your attention.